In this lecture, we're going to talk about a theorem called the law of large numbers. And what this theorem actually tells us is it gets at the meaning of expected value. Let me give an example. Let's say we flip 1,000 coins and let x be the number of heads. We can see pretty easily, if it's fair, the expected value of x is 500. But we also expect in reality for the x should be about 500 or so. That's kind of what we say. When we call it the expected value, that's our expectation. But what does about mean here? Okay, we don't know that we're going to see exactly 500 heads. For example, we would not be surprised to see 503 or 492. We would be really surprised to see 980 heads, however. Can we make this statement precise? What does about mean in this context? That's the content of the law of large numbers. Now we can state the law of large numbers. Let's assume we have a sequence of IID random variables. Remember, that means independent and identically distributed. Let's assume that the mean and the variance of the xi are finite. Let's denote the mean by mu. Let's let Sn be the sum of the first n random variables, and let An be Sn over n. We've defined all these things before. Now for the statement. Choose any positive epsilon. Then the probability that An is further away from mu than epsilon goes to 0 as n goes to infinity. Or, the equivalent statement, the probability that An is within epsilon of mu goes to 1. Specifically for large n, An cannot be too far away from mu. Let's work out what this means in a particular concrete example, where we flip n coins and count the number of heads. A big lemma for the theorem that we're going to prove is this lemma called Chebyshev's inequality. Let x be a random variable with expected value mu. Let's assume mu is finite. Then for any positive epsilon, the probability that the distance between x from its mean is greater than epsilon is less than or equal to the variance of x divided by epsilon squared. We can now prove the law of large numbers using Chebyshev's inequality. Okay, let's go back to a random variable we defined earlier, the binomial random variable. Remember, what we do here is we perform n trials of some experiment, assume each of the trials is independent and it has a success with probability p, and we count the number of successes. This is, of course, a random number, and we like to say something about the distribution.